Hi everyone, it is time for the next lesson in calculus. This is lesson 3.6.4, which is the derivatives of exponential functions. Now, if you have not watched the chain rule video or have done the chain rule homework, I would recommend that you really stop and do that first, because this lesson isn't going to make much sense unless you have done the chain rule work. Because every function that we're going to be talking about from this point forward is going to incorporate the chain rule a little bit. So it's really important that you understand how the outer and inner functions work and how you were able to calculate derivatives using the chain rule. Now, you learned about exponential functions for the first time in 1.3, which was the level 1 tables, equations, and graphs unit. We're going to talk about what an exponential function looks like, what its derivative is, because it is actually one of the easiest derivatives there is. And then we're going to talk about how to do the derivatives of exponential functions that aren't quite so simple. So let's first of all talk about what is an exponential function. It is a function that has a variable of some kind in the exponent, in its exponent. So if the function has the x in the power, it is an exponential function. We are specifically going to focus on one exponential function, which happens to be y equals e to the power of x. If you want to, you can take your calculator and sketch a graph of this function, but I'm going to just sketch it here on paper. Some of you may remember what it looks like. Most of the basic functions go through 0, 0. This is one of the exceptions. When you graph e to the x, it goes through the point 0, 1, because if you substitute 0 into here, e, which is a number, to the power of 0 is equal to 1. We learned that on the first day of this unit. Now, two characteristics of this graph: it has what is called an asymptote, and that's why I'm putting dotted lines at the end of the x-axis. This is called an asymptote, A-S-Y-M-P-T-O-T-E. And what an asymptote is a line that a graph gets really close to but never crosses. So the graph will get really close to the x-axis, but it will never cross the x-axis. It is then also a constantly increasing function, so it is going up forever, but it never crosses the x-axis, so it goes like this. So on the right side, it kind of looks like a quadratic. On the left side, it is getting closer and closer to 0, but it will never get there. Now, the e, to be an exponential function, could be a 2 or a 1/2 or a 5 or anything else. But e is the one we're going to focus on today, because e is the most beautiful as far as derivatives goes function that we can work with. And it is one that shows up in the real world a lot. Now, what makes this unique is the fact that the derivative of e to the x is e to the x. It is its own derivative. Now that's kind of a weird thing to think about. It is its own derivative. And what that means is, and I'm going to draw this in, but I'm going to erase it. If you pick any point on the curve and you draw a tangent line at that point, the gradient of that line is equal to the y value at that point. Let me say that one more time. The gradient of this red line is equal to the y value of that point in question. So let me erase that real quickly. I've got a lot of dots on here, so give me a second. All right, so let's go back to this point right here. If I draw a tangent line right there, the gradient of that tangent line I know is 1, because the y value right there is 1. And it works for every single point on e to the x. So the formal way to write this down is d dx of e to the x is equal to e to the x. The derivative of e to the x is itself. Okay? But that's the only function there is that is exactly that perfect. What if the power is 2x? What if the power is x squared? What if the power is anything else? How do you do those? So if the power does not equal just an x, this is how you do it. It is the derivative of e to the power of u. So u is another function. The way you do this is you have as its answer e to the u again, but then it is times the derivative of the u with respect to x. So that'll make a little more sense once we do one. Another way to write this is e to the power of u times u prime. Now what's happening here is, you remember outer and inner functions from chain rule? In this case, the inner function is the u, the inner function is the u, and the outer function is the e to the power. So when we do the chain rule here, the derivative of outer, e to the bracket, is equal to e to the bracket. And remember, you put the u into the bracket. That's what gives us this first term. And then, after you do that step, you take the derivative of the inner, which is your du dx, your derivative of your exponent. Now, I am one over the years that I've been teaching calculus who likes to give quirky little names to how to remember to do derivatives of things. Okay? So the quirky little name I give to this procedure right here is copy-paste. Okay? You know how on your computer you will you'll highlight a section of text, you'll press Control-C to copy it, and then you'll press Control-V to paste it someplace else? That's what's happening here. We are taking e to the u and we're copying it and pasting it in our answer. That's why I call it copy-paste. So it's copy-paste times the derivative of the exponent. Copy-paste times the derivative of the exponent. That's how you do this. So once we do a few sample problems, I think it'll make a little bit more sense to you. This is the easiest derivative besides the power rule, so that's why we do it next. So let's do a couple of examples. My first function is y equals e to the power of 5x. Okay? So my 5x is like my u. I'm not going to make you change it to a u and then change it back. We don't have to go there. We're going to make it very simple on ourselves. We're going to think what I wrote in red here. Copy, paste times the derivative of the exponent. So when we go to write the derivative, we're going to write y prime equals, we're going to copy and paste the function that you see, e to the 5x, and then we are going to multiply it by the derivative of the exponent only. What is the derivative of 5x? With 5x, you use the power rule. So the 1 power on the 5, bring it down, so it's just 5. So usually, if the derivative of the exponent is a constant, we move it up to the front. So my final answer is 5e to the power of 5x. And that is finished. All right, next example. Y equals e to the power of x squared minus 2x minus 1. Okay, so now my power is a little bit longer. Same procedure, however. If you see that the base is e and that the power is full of x's, we write y prime equals. First thing I see is copy paste, so I just copy and paste the problem. And then I multiply by the derivative of the exponent. Now, because there are separate terms in the exponent, I need to take the derivative of each one individually. The derivative of x squared is 2x minus the derivative of 2x is 2. The derivative of negative 1, being a constant, is 0. So I close my bracket. And this one, because the derivative of the exponent has multiple things in it, we just leave it alone. So that is considered the answer to this problem. All right? Let's do another one. We're going to do a little bit more involved. So actually what I'm going to do is I'm going to give you this one. Y equals e to the power of 4 minus 6x. I would like you to pause the video, and I want you to try this problem yourself. So pause the video, give it a go. When you're done, Turn it back on, and I will work you through the problem. Okay, how did you do? Let's see. So the derivative should be copy and paste times the derivative of the exponent, careful, is -6. So this final answer should be -6e to the power of 4 minus 6x. If you got it wrong, do you understand why you did? If not, pause the video, get on chat, let's talk about it, okay? All right, next problem. We're going to now incorporate a little bit more chain rule into the problem. My new function is y equals bracket e to the x plus 3, the quantity squared. Okay. Now notice this time, this whole problem is one big chain rule like yesterday. Can you identify the outer and the inner functions? If you want to give that a go by yourself, you're more than welcome to. You could pause the video and come back. But I'm going to tell you right now that the outer function is the bracket squared, and the inner function is e to the x plus 3. Sometimes it is easier to write down the inner function first, but it doesn't matter which way you do. Okay? So now what we do when we take the derivative, we have to follow the chain rule because the chain rule encompasses the entire problem. So the derivative of something squared, which is the derivative of the outer, which is 2 something to the power of 1. What goes in the bracket again? The inner function, e to the x plus 3. So we've taken care of the outer function. Now we must take the derivative of the inner function. We do it term by term. So because I see an e sitting here, I copy and paste e to the x. The derivative of this exponent is 1, so I don't need to write the 1 down. And if you remember from the beginning of the notes, the derivative of e to the x is e to the x. The derivative of the plus 3 is 0. So my inner derivative is just e to the x. So you can expand all that out if you want to. Usually you will see the answer this way. They will bring that single e to the x to the front, and they will write the more complicated e to the x bracket at the end. So either one of these two answers is correct. All right, I have one more sample to show you, and then it's going to be time to practice. Last example. Y equals 2e to the square root of x power. Okay. Do we have a chain rule going on here? Well, kind of. First of all, anytime you see a radical, a square root, the first thing you're going to do. Now, I'm going to stay in blue because I'm not actually taking the derivative yet. You rewrite that as an exponent. What is the power of the square root of x? It is x to the 1/2. Okay? So, y prime equals, when you have a constant in front of any other function, when you take the derivative, it is a lazy constant. It just sits there. So I'm going to back up a second. I'm about to take the derivative, so I'm going to start writing in red. Y prime equals, the lazy 2 sits there. And then you take the derivative of the rest of it. So this e term right here is a copy and paste, e to the power of x to the 1/2, times the derivative of the exponent. Now the exponent, remember, is just the x to the 1/2. That is a power function. So its derivative would be, bring down the 1/2, write the x. Remember the shortcut I told you the other day? To find the new exponent, subtract the two numbers in the fraction. Let me blow this up a little. Subtract these two numbers. That is your new numerator. 1 minus 2 is -1 over 2. The bottom number never changes. All right? So I am going to clean this up a little bit, partially because I have a negative exponent. I have all these fractions, and I like radicals. Radicals to me look better. Y prime equals. Now, first of all, do you see that you have a 2 and a 1/2? What are they going to do? They are going to cancel. So we're going to mark those two out. Okay? This e has a positive exponent, so I'm going to leave it on top, and I'm going to put it back in a radical. Now, you honestly don't have to. I just think it looks a little cleaner. Notice the x over here has a negative exponent. Where do things with negative exponents go? They go to the denominator. So I need to draw a fraction bar. I need to put the x down there. It becomes a positive 1/2 power. Or you could write it this way. You could put e to the square root of x over the square root of x, because x to the 1/2 is the square root of x. So that right there is the nice, pretty, cleaned up derivative for this problem. Okay, so I'm going to write this in the notes on the classroom, but I'm going to go ahead and also put it on the video, the assignment for this. So for the practice problems, here's what I want you to do. If you are doing the New Lake 3.6 only, you are going to work on pages 24 to 26. If you are doing the EAS book, you're going to be doing pages 95 through 97. And if you are doing the Delta book, you are doing section 15.03, which is page 268. I would suggest doing the odd problems. Usually it's odd problems are a great way to start to get some good practice in. Please, please, please make sure to check your answers in the back to make sure you are getting the correct answer. Now, you may get an answer that looks different than the back of the book's answer, like these two right here. This one and this one are both correct. They just look very different. If you get a different answer from the back and you can't see how they got it, don't assume your answer is wrong. That's when you ask me. So if you can flick me a photograph or a picture of something showing me, I got this, but the back of the book says that, is it right? I will let you know. Please do not assume your answer is wrong until I check it off. Because a lot of the times, especially with derivatives, there is more than one way to write the answer down correctly. Alrighty, that's the end of today's lesson. Please go to work on the practice. Come back online if you have any questions and let me know. All right, have a great day, and I'll see you later. Bye-bye.